All right, this is a recording, nice. The first set of questions we have is true-false questions. First question is, HCP crystal structures are generated by stacking of hexagonal close-packed planes of atoms in ABC sequence. This is false because the sequence should be AB, 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 right? One question, how much time do you have allotted for this station? I think it's gonna be finished in 1 hour. Okay, so AB sequence for HCP crystal structures, or if you are looking at ABC sequence, it should be FCC crystal structure. In any way, it's a false statement. So strongly bonded materials have a higher coefficient of thermal expansion and higher melting temperature. This is a true statement. The equilibrium separation between atoms can easily be found by finding the distance at which the net bonding energy between the two atoms has minimum value. This is a true statement. Valence electrons occupy the last orbital in each atom, and some of them are shared in ionic bonds between two or more atoms. This is false. Valence electrons occupy the outermost shell, not the last orbital, and also they are not shared in ionic bonds, right? They are there is a transfer of charge in ionic bonds. Sharing happens occurs in covalent bonds. The tendency of a polymer to crystallize increases with increasing molecular weight. This is false. Second question is, we are given some elements and ions, and we are asked to write down the electronic configurations for these atoms or ions. Do you have any questions? You can unmute yourself and ask, or these problems are posted on Canvas. Okay. Can you see my screen? Okay. Then you should speak up. I thought I shared my screen, but I did not share my screen. Can you see my screen now? Okay, this is good. All right. So we went over the true-false questions. Okay. The second question is about the electronic configurations. For the silicon atom, the atomic number is given as 14. In the exam, you will either be provided a periodic table or you are going to be given the atomic number. Okay. So for silicon, we have this configuration. Note that silicon ground state has 14 electrons, 1s2, 2s2, 2p6, 3s2, and 3p2. Now the -4 charge, we add 4 more electrons, and it gets achieves the stable state, noble gas state, right? The argon state. So it has completely filled orbitals. And in the -4 charge configuration, it ends with 3s2 and 3p6. So cobalt is given in the neutral state. It has 27 electrons. So we write down the electrons, 1s2, 2s2, 2p6, 3s2, 3p6. And after 3p6, you can continue writing 4s2, or after 4s2, there are 7 more electrons. So those electrons will go into the d orbitals, 3d7. It doesn't really matter which way you write this. 3d7 may come first, or 4s2 may come first before 3d7. Fe, iron +3. In the ground state, iron has 26 valence electrons. 26 electrons, sorry. So let's write down the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, we are at 18. 4s2, 20, and 3d6, right? You cannot see right now, but it should end with 4s2 and 3d6. Okay? This is for 26 electrons, but we are missing 3 electrons. So those 3 electrons will go from the 4s shell first. We are going to lose those 2 electrons from 4s2 and 1 extra electron from 3d6. So we will end up with 3, 6, 3p6, and 3d5. Okay, match the electron structure below with the element type it represents. This ends with 3s2 and 3p5. So this is a 7a group element, and it's a halogen material. The third question is about the Miller indices and indexing the directions, which is going to be for the fourth question. Third question is about Miller indices. In part A, we are given a cubic structure. And if you remember the algorithm for indexing planes, the first step of the algorithm, if you remember from the slides, is to check whether the plane passes through the origin. Okay? So our origin is here, right? This is our origin, 0, 0, 0. So since this plane passes through the origin, we cannot index this plane. Okay, so we need to move our plane, not plane, sorry. We need to move our origin and coordinate axis to another location. So the choice of the origin, I mean, it's up to you, but when you choose a new origin, make sure that you choose a location such that indexing of the plane will be easy. Okay, what do I mean by that? For instance, if you carry the origin to this point, and if I call this O prime, okay, and let this be my new axis, Y prime, X prime, and Z prime. Okay. So you should be able to see that now this is easy to index, right? I can see that the plane cuts the y-axis at 1/2 and z at -1, right? Here. So, but it's again parallel to the x-axis. It's parallel to the x prime axis. So the first thing I do is to write down the intercepts, right? How do I write down the intercepts? X-intercept, or let's write x prime intercept. It doesn't cut x prime, so I write infinity. Y prime is 1/2, right? And z prime is -1. So this is the first step. The second step is to get the reciprocal. When I take the reciprocal, 1/infinity, 1/1/2, and 1/-1, you will end up with these Miller indices. So 1/infinity is 0, right? 1/1/2 is 2. And 1/-1 is -1, and I write -1 like this, 1 with a bar on it. And be careful, I'm using these round parentheses for the planes, okay, not square brackets. So you can, let me see. You can take this as another origin, right? O double prime. And this is X double prime, and this is Y double prime. And in this way, you can see that the plane cuts the Y double prime axis at -1, right? Here is -1 in this direction. And it cuts the Z axis at 2 here, right? Now, in this case, if I use this point, then I will have again 0, 1 bar, and 2, right? Is that correct? Okay, it's not correct. Anyway, please try to do it yourself. You're gonna get the minus of this plane, which is gonna be the same plane, the parallel plane. The important point here is in the exam, if you are gonna enter any of these, like with this one or this one, 0, 2 bar, 1, you will get the correct answers. These will be correct. These will be counted as correct answers. So for the second part, B, you remember the indexing for HCP structures, we are using this configuration, convention, sorry. X intercept is infinity, right? Doesn't cut the x-axis, this plane. Y, it cuts at -1. And if I get the, let's look at the z-axis. And z-axis, again, this is parallel to the z-axis, right? So it's infinite again. So I take the reciprocals of this, and reciprocals will be 1 over infinity, 1 over -1, and 1 over infinity again. So this will be H. This will be K. And this will be your L. And remember the relation between I and HK. So H, K, I will be equal to minus H plus K. And Z will be 0, 1 over infinity. So this is how we index this HCP plane. All right, let's move on. Determine the indices for the direction shown in the following unit cells. Remember from the slides, the way we do this is we write the coordinates. And this is 1, 0, 0, right? This point. And this point is what? 0, 1, and 1 over 2, right? Then what you do is you subtract tail from head. So this is the head of the vector, and this is the tail. So 0 minus 1, 1 minus 0, and 1 over 2 minus 0. So I end up with -1, 1, and 1 over 2. As a rule, I have to round this to the smallest integer, not round, like multiply by an integer to make these all integers, the indices. So I'm going to multiply these indices by 2. I will end up with -2, 2, and 1. So the way we write this is in square brackets because it's a direction, 2, 1. So use the same method to find this direction vector. It's gonna be 1, 1, -1. All right, let's move on. Any questions up to this point? You can write in the chat or speak up. Okay, question number 5. The Pauli exclusion principle states that each electron state can hold no more than 2 electrons, which must have opposite spins. So this is just a definition question. Sixth question is, calculate the radius of a gold atom. Given that gold has an FCC crystal structure, a density of 22.4 grams per centimeters cube, and an atomic weight of 196.97 grams per mole. Yes, we are given this information and we are asked to find the radius of this gold atom. And in the second part, using the radius calculated in part A, calculate the planar density of the 100 phase. So let's remember this equation for density. Okay. You will be provided these equations in the exam. Density is equal to number of atoms times the atomic weight divided by the volume of unit cell and times the Avogadro's number. So for the solution for gold with the FCC crystal structure, first you should know that the number of atoms in an FCC unit cell is 4. Okay, I guess we don't need to go over that here in this problem session. If you don't know like where that comes from, where the number n is equal to 4 comes from, please look at your slides again. Basically, we have 4 atoms in an FCC unit cell. 1 atom is coming from the corner atoms, and the 3 atoms are coming from the phase centers. So we also know this relation, right? In an FCC structure, these are, you can find this in your slides. 4 times the radius is equal to A, which is the edge length of the unit cell, times square root of 2. So we can write A like this, right? A is equal to 2 times square root of 2R. And then we can find the volume of the unit cell in terms of this R, right? Volume will be A cube, and we can write volume in terms of R, right? 2 times square root of 2 times R to the power of 3. So if you plug in these values in the density formula above, this formula, we know N, we know the atomic weight, which is given, and we can write down VC, the volume of unit cell, like this, right? 2 times square root of 2R cube, and times the Avogadro's number, which is this number. If you do this calculation, and you will find R as this value, 0.137 nanometers, okay? So we found R. The second part of the question is using the radius calculated in part A, calculate the planar density of the 100 phase. So for this part, you need to know like what is 100 plane for the FCC structure, the FCC unit cell, okay? So this is the 100 plane for the FCC unit cell. We have this atom at the center of the plane, and we have 4 corner atoms. And these atoms are actually in touch with each other, okay? This is the reduced sphere model, but the hard sphere model, if you visualize the hard sphere model for the 100 plane, you should know that these atoms along the diagonal, they are in touch, they are in contact, okay? So the side lengths are equal to the unit cell length, and the planar section represented below figure is a square, wherein the side lengths are equal to the unit cell edge length 2r square root of 2. So you know where this comes from, right? I mean, we found it here. Okay. So this is 4r, right? And from this relation, you can write A is equal to 2r square root of 2. And the area of this square is A square, and which is this, right? All right. So what is the planar density? And planar density, by definition, is the number of atoms on the given plane, which is 1, 0, 0 plane, and the area of that plane. So we have how many atoms on this 1, 0, 0 plane? You may answer like, I see 5 atoms, but it's not 5 atoms, because these corner atoms, they contribute 1 quarter, okay? So I have 4 of these atoms, 4 times 1 over 4. The contribution of these corner atoms is 1 in total, and this atom is 1 because it's on the plane. It's totally on the plane. So 1 from the corners and 1 from the face center, total of 2 atoms. And the area of the square is 2r square root of 2 to the power of 2, which is 8r squared. If you do this calculation, you will see that the planar density is 13 plus 32, 10 to the power of 18 atoms per meter square. All right, let's move on. For the calcium fluoride with the rock salt structure, there is incorrect information here. Can someone tell me what is wrong here with this statement? You can write in the chat. Figure is missing. Blue? No. There is nothing wrong with the figure actually, but this is not a rock salt structure. What kind of a structure is this? Okay, you should know this structure. I mean, this is AX2, right? And the formula is given here, calcium fluoride. So this is AX2 structure. This is fluoride structure, not rock salt structure. The example for rock salt structure is sodium chloride, right? Which is AX. So this is wrong. It should be fluoride structure. What are the coordination numbers of calcium and fluorine ions? The coordination number of calcium ions is, if you look at this atom here, which is the calcium ion, it's in contact with these 4 blue atoms, okay? Now, this might be hard to see, but you need to learn the hard sphere model. And this face-centered cation, calcium cation here, is in contact with these 4 atoms at the bottom layer. Okay? So actually there are, if you put another unit cell on top of this, okay, there will be 4 more fluorine ions at the top, like this, in that unit cell. Okay. So basically, I'm translating these atoms here. I'm copying them. So this calcium cation is also in contact with these 4 anions. All right. So the coordination number of calcium plus 2 is 8. Let me clear these. And the coordination number of fluorine ions is, if you look at this unit cell, not unit cell, this part of the unit cell here, this green cube, okay? So this atom is in the center, at the center of this region of the unit cell, and it's in contact with these 4 atoms. 4 calcium plus 2 ions. So that's the coordination number of fluorine ions. So each fluorine ion is in contact with these 4 calcium ions, and the coordination number of fluorine ions is 4. How many calcium plus 2 and fluorine ions are there in the unit cell? The blue ions, you can see they are inside the unit cell, this entire thing. So we have 8, right? And if you don't see the blue cells, blue atoms, if you only see the red atoms, this is like a big FCC unit cell, right? So I have red atoms at the corners and 1 red atom at each face center. So then the number of calcium ions is 4. 1 from the corners and 3 from the faces.
Professor,
Yes.
just to be clear, what simulates a contact is it means that there's no line drawn in between them. Is that what means it's in contact with it?
Yes, that's correct.
Okay, thank you.
I mean, not line, there is nothing such a line, but they are in contact means, I mean, you know FCC, right? You know the FCC, BCC structure. For FCC, we have corner atoms, right?
Yeah.
And I have an atom here at this face, at the middle of this face, in the middle of this face.
Mm-hmm.
So this diagonal, along this diagonal, the atoms are in contact. So what does this mean? If I draw this line, this diagonal, it's actually like this. I have 1 atom here, another atom here, and an atom here. Okay?
Okay.
So yeah, let me draw. This is the red corner, and this is the blue corner. Okay? I'll have the blue corner here and the red corner here. This is what we mean by in contact.
Okay.
So this distance is 4r, right? And what we mean by in contact, you have the same situation here with these ions. This red atom, red ion is in contact with these 4 blue ions. So let me try to draw them from top. If I'm looking at this unit cell from the top, okay. These atoms will be like this. This will be how you will see this calcium ion. It's in contact with these 4 atoms. 4 fluorine ions, okay? It's in contact with these 4. So maybe you can see it like this. It's hard to draw with a mouse. Mm. I don't know. I mean, I think it's not a good drawing, but I think this illustrates better. Put these four ions like this in this configuration, and you can fit an atom, the red atom, which is the calcium ion, such that it's touching all those four fluorine ions. Does that make sense? Okay. Let's continue. Describe the type of bonding for each of the following materials. You should know the solder is an alloy, right? You know what solder is. It's just an alloy of different metallic elements, so it has metallic bonds. Rubber is a polymer. You should know that rubber is a polymer. And in polymers, we have covalent bonds inside the molecules, right? Carbon-hydrogen bonds, they are covalent bonds, and weak van der Waals forces between the molecules. And diamonds, we have pure covalent bonding between carbon atoms. Write the repeating unit for the following polymer. This is the repeating unit, CH2, CHCl, and this is the repeating unit, okay? So what kind of a polymer is this? It's an atactic polymer, which means these repeating R units, Cl, they are randomly located at each site, right? There is not a pattern. They don't take place at one site, or they are not alternating. And this is not a random copolymer, so this is atactic. These are just definition questions. Compute the theoretical density of magnesium oxide, the lattice structure of which is shown in the figure below. B, compute the atomic packing factor. And we are given some data, radius of magnesium +2, radius of oxygen, and atomic weights. So we again use this formula, the density formula, but this time we have two elements instead of like one element like we solved in the previous question, which was gold. We have magnesium and oxygen, but the procedure is the same. Again, we need to relate this edge length. I'm gonna call this A, okay? A, the edge length of this entire unit cell, and we see the volume of the unit cell is A cube, right? So somehow I need to relate this A to the radii of the magnesium and oxygen ions. And how do I do that? I know in this rock-salt structure, this is rock-salt structure, right? These atoms, they are in contact with each other. So there is no gap here between these atoms. This atom, and this atom. If I look in this direction, I will see those atoms like this. So this is the small oxygen atom, and sorry, the magnesium atom. And this is the oxygen anion, right? And I have another magnesium ion here. It will be like this. And starting from the center of these atoms, this is the edge length of the unit cell, right? Which is A. I am looking at these three atoms here. I drove these looking at this in this direction.
Four per atom.
Does that make sense? So looking at this schematic, I can write A like this, right? So A, I have two magnesium radii, 2R, which are these small radii. I have two of these, 1 and 2, and two oxygen radii, 1 and 2. So A is equal to 2R magnesium plus 2R oxygen. So A we find out as 0.424 nanometers. The rest is very similar to what we have done before. Density equation then becomes rho is equal to n prime, atomic weight of magnesium plus atomic weight of oxygen, divided by VC times volume of unit cell times Avogadro number. We need to find out n prime also, like how many oxygen and how many magnesium atoms do we have. You should be able to see that we have 4 of each. We have 4 oxygen ions and 4 magnesium ions. For magnesium, it's easy to see because if you don't see these red ions, you will see that it's like an FCC structure. So we have 4 magnesium ions. And if you count the oxygen ions, you will calculate that it's also 4. So n prime is 4. In the numerator, I write here as 4 formula units per unit cell. And these are the atomic numbers for magnesium and oxygen. And I found the A value, the unit cell edge length before. So this is the volume of the unit cell, and this is the Avogadro's number. Okay. So when you do the calculation, you find the theoretical density value as 3.51 grams per centimeter cube. So calculate the atomic packing factor in the B part in decimal form, not percentage. Atomic packing factor is basically given by this formula, right? Again, you will be given this in the exam, atomic packing factor. The volume of the unit cell is in the denominator, and in the numerator, we have the volume of the atoms, okay? So I found the volume of the atoms with this formula. 4 comes from the number of atoms, right? I have 4 of each of the atoms, oxygen and magnesium. And this is the volume formula, volume of the sphere. And I guess we are given the radii for the atoms, and these are the radii. So this is the total volume of the ions divided by the total volume of the unit cell, and the atomic packing factor is 0.685. Question, so why is the total volume different from part A? Total volume. Is it different? How is it different? So in part A, this is the volume, right? And in part B, this is the volume. I think if you do the calculation, you should get the same values. I mean, it's been some time I did this calculation, but they should be equal. Okay, let's move on to the phase diagram questions. Any questions up to this part? All right, for the phase diagram below, the phase diagram given below, given a starting composition of 38% A and starting from pure liquids, at what temperature would the material first begin to solidify, and at what temperature would the material be completely solid? So pay attention to this part. Given a starting composition of 38% A, be careful, because in our plot, the x-axis is given in terms of weight percent of B, right? Not A. So 38% of A should be equal to 78% of B. So I should be looking at this vertical line here, which gives me the 78% of B, right? So let's look at this vertical line. At what temperature would the material first begin to solidify? Let's say I'm here, okay? I have 78% B in my composition, or 38% A. I'm at, this is 50 degrees Celsius, right? I start cooling down. I cool down, and I come to this point, right? This is the liquidus line. This line is the liquidus line. And beyond this point, if I cool down the material further, I'm gonna start forming the first solid crystals inside the liquid. Okay? And those solid crystals will be what phase? What is this region? This is liquid plus beta, right? I'm gonna start forming this beta phase inside the liquid. The question asks us at what temperature would the material first begin to solidify? So I just draw this horizontal line. I'm sorry, it's not very horizontal. So it's about 650 degrees Celsius, right? So at around 650 degrees Celsius, we start forming the first solid phases inside the liquid. At what temperature would the material be completely solid? So you cool down further. And once you go below this line, which is the eutectic line, right? In this region here, this peak region, you have completely solid phases, 2 solid phases. So the answer is about 600 degrees Celsius. If you cool down below 600 degrees Celsius, which is the eutectic temperature, the material will be completely solid. Given a starting composition of 88% A, again, this is tricky. Be careful, 88% A means 28% B, right? This time I'm looking at this vertical line here. My composition should lie in this, on this vertical line. What phases are present at 500 degrees Celsius? Let's find 500 degrees Celsius, it's here. So I draw this line and the intersection point is here, right? 28% B or 88% A at 500 degrees Celsius. I'm at this cross, okay? So what phases are present in this region? This is alpha plus beta region, right? If you look at your slides in the binary eutectic phase diagrams, so we have this alpha region, pure alpha region on the left and pure beta region on the right, and this middle region is a mixture of alpha and plus beta. So I have both alpha phase and beta phase. Estimate the composition of all phases present at 500 degrees Celsius. So how do I find the composition of the phases? I start from this point, the intersection point. All I need to do is, first I draw this tie line, right? The green line is the tie line. And I find the intersects of this tie line at these solvus boundaries. So this is the intersect of the solvus or this alpha region. And this yellow is the intersect for the solvus for the beta region. All I need to do is, after I find these intercepts, I look at the x-intercept values. And those intercept values will give me the composition of the phases. So the x-intercept here, let me draw it with blue. Whatever this number is, I cannot clearly see. That's the composition of the alpha phase. So let's look at the answer. We need to find the points at which the green tile line intersects the alpha and beta boundaries. The x-intercept values of these points gives us the compositions. Alpha has around 3% of B. So the composition of alpha is 3% B, whereas beta has around 89% B. Okay? That's this intercept, 89% here. So you might ask here, I mean, what if I don't get the exact value? I mean, I show it as like 3%, but what if you enter in the exam 2%? Will you get an incorrect answer? Probably not probably. I mean, I'm not gonna say probably. As long as you give a meaningful result, what do I mean by meaningful? Look at this point, for instance. If you tell me any number between 1, 2, 3, 4, even up to 5, you will get full credit. But if you tell me like this is 10%, 10 weight% of B, it will be incorrect. Okay? So your answer should be meaningful. There will be a high tolerance value for the correct answers. Okay? Similarly for this part. I mean, your answer doesn't have to be 89%. It can be 90, 88, 87, but it cannot be 80, right? You can see that it's not 80%. Okay, in the last part, what is the relative concentration of the phases present at 500 degrees C in weight%? Now we are going to use the lever rule, right? And to find the weight fraction of alpha phase, if I want to find the weight fraction of this alpha phase, I take the part of the tie line which is away from this boundary, which is this region here, Y, okay? This Y part, the Y region of the tie line is away from this alpha solus boundary. So I take that in the numerator. Let me write here, weight% alpha is equal to Y divided by the total length of the tie line, which is X plus Y. Similarly, if you want to calculate the weight% of the beta phase, in the numerator, I take the section of the tie line which is away from this boundary, beta solus boundary, which is X, right? X divided by the total length of the tie line, which is X plus Y. So if you do this calculation, weight percentage of alpha is 80%. And once you find this, you don't need to calculate the beta because they should add up to 100, right? You can directly say it's 20%. Again, the x-intercept values are approximate. You may pick values close and end up with slightly different results, which is acceptable. Any questions? Once you write down how would we use this rule at, say, 650 degrees Celsius, a question. Okay, let's look at 650 degrees Celsius.
That's a good question.
I'm looking at this point, right? Now in this region, tell me what phases do I have? I have liquid plus alpha, right? To find which phases are present, once I mark my point here, I draw this tie line to the left and right once I intersect a boundary, okay? So on the right, I have liquid phase here, right? This region is liquid phase. And on the left, I have this alpha phase here. This region is alpha phase. So this region, this white region, is a mixture of liquid plus alpha. Okay. So let's find the weight fraction of liquid phase first in this region. I'm gonna take the part of the tie line which is away from this liquid boundary, okay? Which will be this part. Let me call it x prime. This is gonna be x prime divided by, if I call this part as y prime, x prime plus y prime. Okay? So similarly, if you want to find the weight percentage of the alpha phase, it's going to be y prime divided by x prime plus y prime. So you need to find the values of these, the real values. What are these? And for that, you need to calculate the x-intercepts, okay? Just calculate these x-intercepts and you need to do some like subtraction and subtraction to find these values, y prime and x prime. All right, let's continue. Same question. Now we have a more complicated phase diagram. This is titanium nickel binary system. The first part, as find and show eutectic points in the diagram. You need to know what eutectic is, like what is the eutectic reaction and what are eutectic points. Eutectic reaction is when you have a liquid phase transforming into two solid phases, okay? And in this diagram, phase diagram, eutectic points are shown with these red dots, red circles. So we transform liquid phase at these red dots, liquid to two solid phases. So let's look here. For this point, liquid transforms into beta titanium because I have this boundary right on the left, beta titanium, and this boundary, titanium 2 nickel. So titanium 2 nickel. So liquid transforms to beta titanium plus titanium 2 nickel phases. Here we have liquid transforms to titanium nickel plus titanium nickel 3, which is an intermetallic shown as a straight line, right? Which doesn't have a region. It's shown with a straight line, which means you can only have this composition at a single composition. Titanium nickel plus titanium nickel 3 liquid. And here we have liquid transforming into what phases? Titanium nickel 3 and nickel, basically, okay? Okay, I mean, these were not asking the question, but this is just extra information. For a system with 15 weight percent nickel at 1200 degrees C, whenever you see a phase diagram, you are going to be asked 3 questions. What are the phases present? What are the compositions of those phases? And what is the weight fraction of each of these phases? Okay. So I'm going to solve on this B part because we don't have too much time. So 15 weight percent nickel, I'm going to be looking at this blue line, right? And the temperature is given as 1200 degrees C. So this is my temperature. Basically, I'm looking at this green dot here. What phases are present? You just read from the diagram. Actually, the diagram doesn't show you anything. It's an empty region, but you need to find the phases in this region. So what you do is you look at left and to the right. You read the phases to the left and to the right. On the left, we have beta titanium, right, in this region. And on the right, we have liquid. So this region is a mixture of beta titanium and liquids. So we have beta titanium and liquids. What are the compositions of those phases? To find the compositions, we find the intersects with these boundaries. And we look at the x-intercepts, these dashed lines. And these will give us the compositions. So the orange line, this vertical line, gives the composition of the beta titanium, which is roughly 88%, right here. And for liquid phase, nickel content is around 23% here. Okay. And what is the weight fraction? Like we have done in the previous question, you apply the level rule. Okay. You find the values of these x-intercepts and you calculate A and B as values. Then you use the level rule. Weight fraction of beta titanium is B divided by the part of the tie line which is away from the beta titanium boundary, divided by the length of the tie line. And similarly, for weight fraction of liquid phase, we have A divided by A plus B. All right, yeah, you can solve the C part similarly. I'm gonna post these answers after the session. So another phase diagram question. Again, we are asked to find the composition at the eutectic point. In the iron-carbon phase diagram, eutectic points, remember the definition, liquid goes to two phases, two solid phases. It's this point, this is the eutectic point. And eutectic reaction is at 1147 degrees Celsius. At 1147, we transform liquid to two phases, two solid phases here. Eutectoid point is when you have one solid phase going into two solid phases, different. Part C of the last question, I did not do the part C of the last question because it's the same as part B. I mean, I'm gonna give out these solutions. Okay, just apply the same procedure and you will find the results. So the answers are here, okay? Well, actually, you don't need to do anything for part C. Let's go over part C. I forgot this part. Okay. So for system with 58% nickel, again, what you need to do is you find this composition here. This is 58%, right? And you look at 1000 degrees C, and basically you are at this green point here, right? So this is actually not similar to B. This is a very easy question. What phases are present at this point here? I'm in this region. This is a single phase region. You should be able to see that it's a single phase region, right? It is titanium nickel. So I have only one single phase, which is titanium nickel. This is not a two-phase region. What are the compositions of those phases or that phase? Since we have only single phase, the composition of that phase is 58% nickel. And what is the weight fraction? Since we have only one single phase, it's 100%, right? It's 100% nickel titanium. Okay, for this iron-carbon phase diagram, the composition of the eutectate point is 0.76 weight percent carbon. We are here, eutectoid point, one solid to two other solid phases. What is the lowest melting temperature an iron-carbon alloy can have? To be able to answer this question, you look at this liquid region here. Okay. This is the liquid region. Okay. So as you can see, this 1147 degrees Celsius is the lowest melting temperature an iron carbon alloy can have. So what is special about the value 2.14 weight% carbon? Again, this is a set value, it's a definition. If the composition of carbon is less than 2.14 weight%, then the alloy is called a steel. If it's greater than 2.14 weight%, it's called a cast iron. So this question is very similar to the previous questions we did for nickel titanium. I'm gonna solve only one part again. For a steel with 2 weight% of carbon, note that we are given the composition, right? We are given that the carbon content is 2%. What is the concentration of carbon inside the austenite phase at 800? Pay attention, we are given the temperatures and 1200 degrees C. Let me draw this vertical line. This is my vertical line. And let me draw these horizontal lines corresponding to the temperatures. This is the first temperature and this is the second temperature, right? 800 and 1200. Let's look at the intersecting points. Start with 800. What is the concentration of carbon inside the austenite phase at 800? So I'm at this point. So to find the concentration of carbon, I just need to draw this tie line, right? To the left and to the right, all the way to the border of cementite. But I'm concerned only about this intersect because the question asks me the concentration of the gamma phase, austenite phase. Okay, so I find this intercept and I draw this vertical line. And I find the result is about 1%. So at 800 degrees C, the concentration of carbon inside the austenite phase is about 1%. See, this is the answer. And let's do the same thing for 1200 degrees C. Now I'm at this point and I draw this tie line again and I look at this intercept now. So the answer is about 1.7% carbon at 1200 degrees C. Okay, so again, don't worry if you are off by a few percent, it's fine. I mean, it's going to be accepted as the correct answer in the exam. For a steel with 3 weight% carbon, 3 weight% carbon, how does the concentration of carbon inside the austenite change compared to the steel with 2 weight% of carbon at the same temperatures? Okay, let's draw our line again. 3 weight%, right? I'm here. For a steel with 3 weight% of carbon, how does the concentration of carbon inside austenite change compared to steel? I can take any point. I mean, we are not given anything about the temperature, so I'm just gonna pick this point, okay? Because in this region I have austenite, right? I have a mixture of austenite and cementite. Okay. So let me find the concentration of carbon inside the austenite phase at this point. We do that by drawing a horizontal line, right? So this is, and when I draw the intercept here, this will be the austenite concentration of carbon in the austenite phase, right? I draw this horizontal line. I look at this intercept at the austenite boundary, and it's about 1.5%, let's say. This is for a steel with 3 weight% of carbon. So how does the concentration of carbon inside the austenite change compared to the steel with 2 weight% of carbon? So if I don't change the temperature, but I look at this time a steel with 2 weight% of carbon, I'm here, right? This time. This is 2%, this is 3% carbon, the nominal composition. But I do the same thing to find the carbon content in the austenite phase. Again, I draw this horizontal line, and I'm going to find the same result, 1.5. So the answer is no change in austenite composition. Compositions of the phases are not changed within the two-phase mixture region at a constant temperature. The only thing that changes is the amount of each phase in the mixture. And you will see that because if you apply the lever rule, you will see that these levers, like the regions of the levers, will be different if you want to find the weight percentage of different phases. So the composition will not change, only the weight percentage will change, weight percentage of the phases. Okay. And this is the last question. Again, it's a phase diagram. For some iron carbon alloy, the mass fractions of total ferrite and total cementite are 0.55 and 0.45 respectively. On the basis of carbon content, is this alloy classified as a steel or cast iron? So we are given the mass fractions or weight fractions of total ferrite and cementite. We are not given anything about the composition of the alloy. Okay, the phases are given. Pay attention. We are given total ferrite and cementite. So wherever I am at what temperature and composition, I have ferrite and cementite. So if I look at this phase diagram, the region where I have ferrite and cementite is this region, right? So I need to pick a point somewhere in this region so that I have ferrite and cementite. I pick an arbitrary point, okay? You can pick this C0 anywhere you want. I pick it here because the weight percentages are given as 0.55 and 0.45. So it's about the same, right? I mean, we have like 55%, 45% of each phase. So we should be somewhere near the middle of the tie line here. Our tie line is purple line, right? This purple line is our tie line. Okay, I call it C0. I don't know the composition. I'm gonna clear my drawing. To be able to find the weight percentage of alpha phase, what do I do? Alpha phase is here, right? On the left, sorry. I take the region of the tie line which is away from the alpha solvus boundary. So I take this region. Okay. This region, I know the length of this region is, I know this value here. This is 6.7. And this is C0. So here, this length is 6.7 minus C0. Okay. So by lever rule, the numerator will be 6.7 minus C0 divided by the total length of the tie line, which is 6.7 minus 0.022. I mean, this 0.022 is actually this value here. The actual value can be slightly different than this, but it's not very important. It's a very small value. It's not going to change your results. So if I make the calculations, what do I get? This weight fraction is given, by the way, in the question. This is weight fraction of ferrite is 0.55, right? So this W alpha is 0.55. Now, using this equation, I can find C0 as 3.03 weight percent of carbon. So the actual composition is somewhere here. Okay. So is this alloy a cast iron or a steel? Remember the definition. If the concentration of the iron carbon is larger than 2.14 weight percent, this is called a cast iron. So this alloy is a cast iron. Okay. What else? If the alloy is steel, is it hyper? If it's a cast iron, is it hypoeutectic or hypereutectic? So again, this is a definition. This is our eutectic point, right? 4.3%. If your composition lies to the left of this composition, if the carbon content is smaller than 4.3, the composition is hypoeutectic. And to the right, if you have carbon content more than 4.3, this is hypereutectic. So our composition is a hypoeutectic composition, right? Yeah, because this composition is 3.03% is less than the eutectic, the alloy is a hypoeutectic one. So that's it for the problem session. These are all the questions we had. I'm gonna stop the recording here. Let me see. Stop recording.